Okay, let's do a few more examples of how to draw Lewis structures using the Lec16 shortcut. Alright, so we already talked about dinitrogen and we arrived at the correct Lewis structure using the shortcut. Now, there's a few extra addendums to the rules that need to be addressed because they will play a role in terms of getting the correct structures for other elements. First things first, if the central element is second row, meaning nitrogen, carbon, um, yeah, pretty much those guys, and oxygen, you have to abide by the octet rule. And now here's where I kind of sort of bypass the idea of using the formal charge formula. Um, this you can only do if you're starting from scratch for the formula, but if you already have a Lewis structure drawn out for you, you have to use the full length of the formal charge formula in order to find out the charges. But as long as you're starting from scratch, if you have a molecule that has a positive charge or a negative charge, the way in which you introduce charge into the Lewis structure, following my set of rules, is by increasing the number of bonds, in which case you will increase the charge, or decreasing the number of bonds, in which you decrease the charge. Now, what's important to keep in mind is that when you decrease the bonds, you can only do so up until the point where you have a single bond left over. At that point, you cannot decrease the bond length anymore, because if you do that, you completely disrupt the connectivity between the atoms. So, just make sure that when you're decreasing the bonds, you go after multiple bonds, right? You could decrease a triple bond to a double bond, or you could decrease a double bond to a single bond, but don't be decreasing single bonds to nothing. That would be bad. But this is how you introduce charge. So if you increase the bonds number by 1, you increase the charge number by 1. If you decrease the bond number by 1, you decrease the charge by 1. And by following my rules, automatically the charges of the external elements are all 0. So this rule number 2 gives you a means for increasing or decreasing the charge of the external element. The last one is that if you see hydrogen in connection to oxygen in an oxyacid compound like perchloric acid, for instance, you must make sure to bind the hydrogen to one of the oxygens. And if you have multiple hydrogens in your oxyacid, then each one of those hydrogens will have to be bound to a separate oxygen. All right, now with all of this, let's see what we can do in terms of um, drawing Lewis structures. So here goes example number 1. We're looking at nitric acid. All right, so for nitric acid, we have a number of atoms. What we need to first do is identify the central element, and we will notice that the element present in the least amount, well, there's actually 2 of them, hydrogen and nitrogen. There's only 1 of each. So what you then do is look at the element with lower electronegativity. Now, that would basically mean that you will go with hydrogen, but here is where this is the unwritten rule in my set of rules. Hydrogen, you can only draw a single bond to it, meaning that you can never make it a central element, at least not for the molecules that we're going to be investigating in this class. So I want you to think from this point on that hydrogen is going to be an external element, period. And not only that, it will only have a single bond, and that's the end of the story. No lone pairs, nothing. Just a single bond to some other element, but hydrogen will be external. So even though, technically speaking, hydrogen is the element of lower electronegativity, it doesn't meet the criteria for being a central element because it's technically an element that only possesses the first energy level, and it can only have at most 2 electrons. All right, so with all that being said, we're sticking with nitrogen as being the central element. Second thing, since this is an oxyacid, the hydrogen anyway is going to be bound to one of the oxygens, so it's going to be external from the get-go. So what that means is that nitrogen is our central element. So what I basically do is I write nitrogen in the middle. I put the other 3 oxygens around nitrogen, and the hydrogen has to be bound to one of the one of the oxygens. Which one? It doesn't really matter, but it'll be bound to one of them. All right, now with that premise and that skeletal form in place, we move on to the next step. The next step says that we're going to determine the number of bonds from the external elements to the central one based on the formula here, 8 minus group number. Okay, so oxygen is in group number 6. Oh yeah, and one more thing. This is me just being cute with the equation for hydrogen, but the truth of the matter is that you don't even need to do an equation. Hydrogen will always be singly bonded to the oxygen or whatever other element is bound to. Okay, so only one single bond for hydrogen. That's the end of the story for it. Okay, but for the oxygens, the story is that we have to subtract the group number from 8. And the group number of oxygen is 6. 8 minus 6 is 2. And what this tells us is that oxygen needs to have a double bond or collectively 2 bonds present on it. So for the oxygens that have no other atom bound to them, automatically what you want to do is draw a double bond onto the central element. Now the oxygen here that has the hydrogen bound to it, it already has a single bond present. So you only need to have a single bond attached to the central nitrogen element for the oxygen here on the left to have 2 bonds altogether. Okay, so that's the one caveat, right? So if you have further connectivity, you have to account for all the bonds present on the oxygen. Don't just go automatically drawing the double bonds. All right, now if you look at the central atom and you subtract number of bonds from the group number, the group number of nitrogen is 5. And if you count right now, we have 1, 2, 3, 4, 5 bonds around it. So technically, yes, and here we go, nitrogen is in group 5. If you subtract 5 bonds from the group number 5 of nitrogen, we get 0. And that means that you have no addition of electrons on the nitrogen that needs to be accounted for. But here's a little problem. The problem is that the central element, nitrogen, is indeed a second row element. So that means that you have to abide by the octet rule. So what we have right here, unfortunately, is a problem, right? Yeah, so nitrogen, as you can see here, is on the second row. If you count how many electrons nitrogen has by simply multiplying the number of bonds present on it by 2, we find out that we have 10 electrons of nitrogen. And basically, if we were to leave the structure the way it is, we will have violated the octet rule. So what this means is that we need to decrease. We have right now way too many electrons of nitrogen. So we need to decrease the number of bonds so that we decrease the overall number of electrons of nitrogen. And if we basically decrease the bond by 1, so notice what I did right here. I took the double bond that I had on this oxygen on the right side. I decreased it from 2 to 1. And now the nitrogen count is 8 electrons. So that's pretty good. But because I did decrease the number of bonds of the external oxygen here on the right from 2 to 1, that means that the charge of oxygen is decreased from 0 to -1. All right, so this is looking pretty good. All right, now if you look at nitrogen, basically what you want to have is 3 bonds based on the formula, right? So A minus group number tells you that you want to have 3 bonds around nitrogen, and instead what we do have here is 4 bonds around it. So what that means is that we have increased the number of bonds of nitrogen from what we would like to have, and as such you actually have increased the charge to +1. So it's kind of a nice little way of arriving at the charges. In a separate video, I'll kind of address this issue or this idea a little bit more, because it's an important one to keep in mind, and formal charges are going to play a huge role in the context of this lecture anyway. All right, now at this point the central element is happy. We have 8 electrons on it. We haven't violated the octet rule. What's left to be done is that for every external atom other than hydrogen, we need to complete the octet rule. So if we look at the oxygen here on the left, we have 2 bonds on it. So that means that we have 4 electrons on it as of now. We are missing 4 electrons. So what we do is we input the 4 electrons as 2 lone pairs of electrons. And here you go. You have your 2 lone pairs on the oxygen. Looking at the oxygen here on the left, pointing down, we also have 2 bonds. So that means that we have 4 electrons on the oxygen. We need to add 4 more in order to complete the octet. So we add them as 2 lone pairs. And finally, the oxygen here with a negative charge, we have only 1 bond present on it, so we only have 2 electrons. And that means that we are missing 6 electrons altogether. So we add them as 3 lone pairs around the oxygen. And the moment you do this, you have arrived at your Lewis structure for nitric acid, which happens to be a structure that has a negative and positive charge within it. We call this a deuterionic compound. All right, now one more thing I want to show you. We kind of bypass this. This is kind of the first thing that you do when you follow Lewis structures the typical way it gets taught. That if you look at the number of valence electrons, we have 1 for hydrogen, 5 for nitrogen, and 6 for oxygen. If you multiply each of those valence electron numbers by the corresponding amount, 1 for hydrogen, 1 for nitrogen, and 3 for oxygen, we find out that there is 24 valence electrons. And if you count the number of bonds present in the formula, which is 1, 2, 3, 4, 5, and the number of lone pairs, 1, 2, 3, 4, 5, 6, 7, we have 2 times 5 plus 2 times 7, which is the same thing as 10 plus 14, which is 24. So without even looking at the number of valence electrons, using my shortcut, you automatically get the correct number of valence electrons. And this is the power that I think comes with using this method. Okay, in the next video, I'm going to show you another example of using my method to derive Lewis structures. So see you in the next video.